Hello everybody. Alright, so today we're gonna start looking at sampling distributions. But before we get to that fun part of the day, I want to show you some ways you can double check some of your work. In chapter 3 we dealt a lot with z-scores, so let's take a look at some of the information we can deal with. So to calculate z-scores, this is what you would have to do if you didn't have a table or a calculator available to you. Again, on the exams you will be afforded a table, so this is not what you're gonna have to do, but just in case you're interested, this is the function that makes that graph possible, and this is the calculation for the area. We're not going to worry about it, so bam. So there's some z-scores calculators available online. One is here when we dealt with 1.28. So if we click show explanation and continue, it actually shows you all of the needed parts. It tells you that the probability above 1.28 is equal to 1 minus probability that is below. It calculates this. It shows you all the steps, and if you really want to know, here it is. It shows you how to find it on the table as well. So this mathportal.org seems to be one of the neat tools you can use to help you deal with problems in statistics. So that's one of the recommendations. Again, this starts with z's, but if we look at a different one, that's the problem we did in class or in one of the lectures. I think the previous one. Again, the mean, the standard deviation. Are we talking about values that are less, more, in between? I like to leave the show explanation, compute. And again, it shows you a picture, shows you where the value is. Mind you, this is a normal distribution. This is not a standard normal. You would need a z-score to have a standard normal. And it does the calculation for you. And visit z-score to look the z-score calculator up. And then if we click on visit the z-score, right, we get back to what we were. So again, the tools are available. And then the social science statistic calculator, again, just has a quick z-score calculator, and then you can use that. So they have a long list of calculators available, critical values, confidence intervals, whatnot. So they have a whole list of here, and then they have, again, means, modes, and histograms available to you as well. So they have, again, information available. Okay, so let's look at sampling distribution. And the sampling distribution, okay, this is the dead pen from last time. Let's see. So sampling distribution. So sampling distribution is the idea that rather than looking single data values, we are going to use a sample to estimate the population. So what we want to do is we want to take a sample and be able to talk about the population using the information we got from the sample, right? So we want a sample statistic, going into some population parameter, right? And that's the basic idea for chapter 4. We're done. Now, to do this, we need to start considering all the possible samples we can take. So if we have a population size n and a sample size n, how many samples can we take out of the population? Well, if you remember chapter 1, this should come to mind, right? And we can very quickly realize that if our population is size 20 and our sample is size 6, that number will get very large very quickly. In this case, 20C6 ends up being 38760. So this is very, very large. Excuse me for a second. I'm sorry about that. When there are people coming in and out of the house, sometimes I want to check if they're not robbing my place. Alright, so anyways, if we have population size 20 and we want to take all possible samples size 6, we would have to take 38,760 samples. So the question comes, why not just run a census on 20 values, right? Even if we decided to make it look like this number is going to be interestingly huge. Yeah, that number is about 7 with 51 zeros. Like, why would you even? What the hell is going on? And here's the juicy part. If we want to take all of them, that would be insane by comparing how big the census is. But these samples are going to look a certain way, and this is the cool part. So hang in with me, we're gonna get to something really cool very soon. So if we consider a sampling distribution of what? Well, of some statistics. What kind of statistics did we cover? Well, we covered means, proportions, variance, standard deviations. But let's look at, say, means. Right? If we look at this, and we assume we take all of the statistics, right? All of those samples. So assume you take all the possible samples, and I mean all of them, 38,000 or whatever that number is. All the possible samples of size. Well, we need to specify the size, so in this case we're going to say size n. Find the required statistic, right? So if we are talking about means, we're going to find all the possible means, and then we organize them into a chart or table or anything else. I mean, we would have built a sampling distribution. So that's the basic idea. We take all the possible samples, we arrange them in some kind of table or a chart, and this is the sampling distribution. Now, why the hell would we do that? Well, this is because we claim intuitively that a mean of a sample is going to estimate a mean of the population. How well? We don't know, but this is going to happen. So here's an example I have for you. I created a spreadsheet which has the following features. Each one of those cells, and there's 310 of them, rolls a random die between 1 and 6. And I roll 100 times for each row. So there's just a huge table of dice rolls. And if we consider taking just those random rolls, 310 of them, I believe, and we generate a histogram which has 6 classes, what we're going to get is something that looks relatively uniform. Right? There's about as many 1s as 2s, as 3s, as 4s, as 5s, and 6s. Now, there's some variation again because there's only 310 rows, but eventually this thing would kind of plateau. So we have this population of rows, and again we can do it. Now I am going to start running samples. First set of samples for this is going to be the first column, and the first column acquired the sum of 10 rows, and here's the sum of those 10 rows, and that sum of 10 rows. What would be expecting the average to be? Well, if you roll it 10 times, you would expect the average to be what? What's the average of a dice roll? What do you expect as an average for a dice roll? Well, you can get 1 plus 2 plus 3 plus 4 plus 5 plus 6. 10, 20, 21 divided by 6. 21 divided by 6, 3.5. So we would expect a die to produce 3.5. Okay, so if we roll it 10 times, we would expect, so for one die, one roll, we would expect 3.5. For 10 rolls, we would expect 35. For 25 rolls, we would expect 87.5. And for 100 dice, the average would be 350. So this is what we're expecting. And again, let's take a look. And if you look at these numbers, they're about 35. Oh, they're a little higher, a little lower. So we're going to generate a histogram. We're going to make sure that there's 6 classes. And look at the shape. Whoop, whoop. That's kind of interesting, right? And most of them end up somewhere between 32 and 35. All right, let's keep on going. Let's say I'm going to look at the average of the average sum of 25 rolls. And again, I would expect about 87.5. And not bad. Generate. Again, those are random numbers. I'm going to make sure that we have 6. And look at that. This shape, right, starts looking more and more interesting. And then finally, 100 rolls. So sum of 100 rolls generate. And again, we're gonna get 6. Look at that. I think it's kind of cool. I think it's kind of cool the fact that we went from this to this to that and to this. Now again, those are just generated on our possibility. We could, force specify, class ranges and whatnot. So there's some things we could do it, but just sheer generation of a very simple histogram. See what we're getting? And this, I think, is really cool because this brings us to the idea that maybe if we got to kind of this set of numbers, right, we would be able to get some good estimation. Well, how do we know it's a good estimation? Well, again, I'm going to look at, this is the 100 roll setup. What's the mean? 349, and we would expect 350. Huh, interesting. Well, let's look at the second one. This we were getting 86.78, and we were expecting to get 87.5. Close, right? And then we got 35. We would expect to get 35, and we got 34.67. And then the last one for just single rows, we would expect 3.5, and we got 3.45, which means that we're getting from this collection of those samples, we're getting a mean that is very representative of what we would expect to get from this population. Right? We would expect to get about 3.5, right, per die. So if you have 100 die, we would expect 350 as a sum of it. And we got 349.28. And if I kept on going and going and going, eventually this number would be very close to this 350 that we established here. All right. So having this kind of experiment in mind, we can achieve this kind of feeling that the sample mean, right, estimates or targets a population mean. And this is big, because if it works for means, it's going to work for proportions as well. Right? So sample mean estimates population mean. Sample proportion estimates population proportion. Sample variance estimates population variance. Standard deviation is a little tricky for another set of reasons, and we're going to cover that later. But this idea starts working. So when we start talking about all those possible samples, we are not planning on taking all the possible samples, but we have a vague understanding that those samples are going to behave a certain way. So what we need to introduce now is something called the central limit theorem. And for that, I'm going to get a new marker. All right, so central limit theorem. Central limit theorem. Central limit theorem says the following. For a population with mean mu and standard deviation sigma, we can take a sample that is large. If we take a large sample, and again we took that large sample right here, size 100. If we take a sample, large sample, the sampling distribution of what? Well, of sample means is normally distributed. And that's important, right? Means that whatever the population was, and in our case the population of dice rolls is uniform distribution, right? Whatever the population distribution was, if we take a sampling distribution where our samples are bigger than 30, we are going to get normal distribution. And this is pretty normal. Now again, I could say, hey, I want 10 classes, and look at that. That is pretty normal. Now if I want to get 3 classes, again, this is very normal looking, right? So this idea is spectacular. And then what we realized is that if we take a mean of those samples, we're gonna get the population, right? We're saying here, if we have 100 dice with a mean of 3.5 per die, that's what we got. We should get getting 350. Well, what did we get on ours? 349.28, right? Which means that if we take an average of those samples, we should get a population sample. Now again, here I say I'm gonna take an average of all the sample means. We didn't do that. We just took a small section of it. But right, this is kind of cool. We only take 300 of those samples, but this is cool. The reason why it's cool is because an average of sample means we can get a population mean. The other thing we can do is the distribution of sample means equals to the population distribution divided by square root of n. Right? Standard deviation of sample means equals to the population standard deviation divided by square root of n. And again, I find this really fascinating because it means that the data is less spread around. Well, let's see. This is very spread around. And this is less. And less. And eventually less. This is getting tighter and tighter together. So we go from a distribution. In our case of our die, we went from a distribution that looked like this to a distribution that looked like this. Again, we are talking about roll of dice, but this applies to a lot of other normally distributed things. It applies to normally, but then we get a large sample, and this starts applying to all of it. If we have a distribution that looks like this, the sampling distribution of this with a large sample look like this. Because the chances of getting all big values in a sample or all small values in a sample is very small, right? What you're going to get usually is some of the big ones, some of the small ones, and they're averaging right here in the middle. So this is case number 1, and I find this very cool. Case number 2 says, hey, we're going to take a small sample. But for that, the population is normally distributed. So we're talking about this case, where we have a normally distributed this, and then we take a sampling distribution just tightens everything up. Well, in this case, the sampling distribution of, well, in this case we're doing sample means, so sample means is also normally distributed. And if that is true, then these two conditions also apply. Alright, is there a third case? What happens if we don't know what's going on? Well, if we take a small sample, if we take a large sample, we don't care. I don't care what the population looks like, I'm just taking a large sample and I'm good. If I take a small sample, I care if there's a normal distribution. If n is smaller than 30, so it's a small sample, and we are doing a Jon Snow when we know nothing, about the population, well, then we're kind of screwed, at least for now. We can't do it yet. Alright, so we have those 3 cases. So let's go back to our sample mean population. Well, before we had a z-score that we used extensively to do this, and for an individual piece of data, that was brilliant. There is a downside, we need to know the mu and the standard deviation, but we're going to deal with that later. Now, we no longer want to use a single piece of data. We want to use a sample. Well, we don't have a data value, we have a sample mean. Well, in that case, we don't have a mu, we have a mu of sample means. And we don't have a standard deviation, we have a standard deviation of sample means. Oh my god, such a difficult formula. But if you consider the fact that in both case 1 and 2, this is that, right? If we consider those two, then our z-score becomes just x bar minus mu divided by sigma divided by square root of n. Or if you prefer, and that might be easier to type into a calculator, dividing by a fraction multiplying by its inverse. So those two things are equivalent. And this is for an average of a group of values. And by a group, I mean a sample. Now again, we still have to know the population mean and the population standard deviation, so there's some steps for us we need to go through, because otherwise we cannot do it. So why take a sample if we know the population? But if you're willing to squint your eyes for a little bit, we're gonna get to how to find mean and standard deviation very soon. Alright, so here's the juicy part of this. How do we do it? I'm gonna put this over here, this over here. So imagine we have, actually, how do I do it? Right, let's do this maybe. Put this here. So little desk space, so many problems. Alright, let's consider the following two problems. I'm going to write them out big. I'm going to put them next to each other. I'm going to solve them too. So there's two problems I want to look at. First one is saying that a population of men has a mean of 172 pounds. Again, we're talking about weight. And a standard deviation of 10 pounds. And I'm asking you to find probability that a randomly selected man will weigh more than 175 pounds. Weight is normally distributed. So that's question number one. Question number two is a population of men has a mean of 172 pounds and a standard deviation of 10 pounds. Find probability that a group of 20 men will have an average weight of more than 175 pounds, and again, weight is normally distributed. And that's problem number two. So what's the difference? This is the question, where is Waldo? Now you can pause the video and try to figure it on your own. So I'm going to give you 5, 4, 3, 2, 1, and here it goes. So first things is, here is randomly selected men, a group of 20. So that's first thing. Second one is, we'll have a weight. Well, we'll have an average weight. Right. These are the two big things here. It's the group and an average, single individual and a single value, and the rest of it looks the same. Now, because we have a sample that is smaller equal to 30, we need to know if it's normally distributed, and it is. Right? So our z-score for this is x bar minus mu divided by sigma times square root of n, and we have a z-score for this, which is x minus mu divided by, this is chapter 3, this is chapter 4. Alright, well, let's solve it. This is 1, this is 2. Actually, I'm going to maybe put them like this next to each other. So, chapter 1. Z-score equals to x minus mu divided by sigma. So, our z-score equals to 175 minus 172 divided by 10, which comes out to be 0.3. Then we draw our picture. We realize that 0.3 is here. Which area are we looking for? We're looking for more. And the more is here as well. More. So we're looking for this area. We look up our z-score table and we get that this is 0.6179. Well, so how big is this one? This one is 1 minus 0.6179. So our probability of finding an x greater than 175 equals to 1283, 38.21%. There's 38.21% that we're going to randomly select a man who is 3 pounds over the average. So let's take a look at the other side. The other side says z equals x bar minus mu divided by sigma times square root of n. So our z is 175 minus 172 divided by 10 times square root of 20. So our z-score comes out to be 1.34. We want more, so this section, we look up 1.34 and we get that this area is 1.9099, which means that this area right here is 1 minus 0.9099. So the probability of finding x bar bigger than 175 comes out to be 10900. So it comes out to be 9.01%. The probability of selecting a group of 20 men whose average weight is more than 175 pounds is 9%. How the hell did that happen? How the hell we got from 38 to 9%? Well, very simply, just like with the dice rolls. What's the probability of one die rolling a 6, 1 out of 6? What's the probability of rolling 20 dice with 6s on it? Extremely small, right? So if we can find somebody who's really, really heavy, there's a good chance we're gonna pick somebody who's very, very light too. Because here I'm not asking for every man to weigh 175 pounds. I'm talking about the average. So if we picked up somebody who weighed 400 pounds, right? There's an off chance we're going to pick a couple people that weigh 150, 160 pounds. And once you add up all 20 values and you average them, well, you're going to get, right, this number getting skewed. The average of those. Why? Because we took a sampling distribution, which means that we're getting tighter around, right? It's easier to find one individual away from the mean than to find 20 individuals whose average is away from the mean, because the whole distribution got tighter and tighter. There's one thing we forgot to do, is we forgot to check for conditions, and that's the first thing you need to do before you actually solve it. Check if it's smaller or greater, and then check if it's normally distributed. Alright, how was that? I thought that was pretty cool, and I thought that was, very doable. Again, chapter 3 kind of problem, chapter 4 kind of problem. Alright, let's try one more. I like zombie movies. I don't know about you guys, but I like zombie movies. I like movies where things give chase. So World War Z was nice, and Train to Busan was one of my favorite. But the thing about zombie movies is that all zombie apocalypse start very simply. They start by just a little skew things. So the example I have is that body temperature has an average of 98.6 degrees Fahrenheit, if I remember correctly, and it has a standard deviation of 0.62 degrees Fahrenheit. So imagine a sample of people. How big? Say 106. So a large sample of people was selected at random. Again, we're not doing convenient sampling, we're doing random sampling always, even if it's not said so. So what's the probability that average temperature for the sample will be more than how much more? Say 2 degrees, 98.8 degrees Fahrenheit, 2/10 of a degree. Well, let's see. We have n equal to 106, and because we have a large sample, we don't care if the temperature is normally distributed or not. We have a mean of 98.6. We have a standard deviation of 0.62. And we have our average. This is not a value, this is an average of 98.8. Can we do this? Yes. This is condition number 1, large sample. Because it's a large sample, we can keep on going. So z equals x bar minus mu divided by sigma times square root of n. So our z equals to 98.8 minus 98.6 divided by 0.62 times square root of 106. On a calculator, the easiest way to do it is 98.8 minus 98.6. Press enter. Let's see if we can. So I did the first calculation. Then after that, I'm gonna divide it by the standard deviation. Enter. And then I'm gonna multiply it times square root of 106. Enter. So do it stepwise. First, second, third. And that comes out to be 3.32. All right, 3.32. All right, well, what's next? Well, next is this. Where's 3.32? Say it's here, 3.32. And which area are we looking for? We're looking for more. So we're looking for this. Okay, so let's take a look at. So, boom. We're looking for probability of a z-score being bigger than 3.32. 3.32. Compute. This is telling us that this area is 0.9995, which makes this area 1 minus 0.9995, which makes it 0.0005. Right, we're looking at 3.32. So this is the 2, this is the 3.32, and here's the number. And because we're looking at this area, we have to do 1 minus. And that comes out to be, right, so we're looking at this area, above that. Alright, which means that the probability that the average temperature is going to be more than 98.8 degrees is what? Is 0.05%. 0.05%. Which means that if we know that this is the average, this is the standard deviation for the population, we know this is true. We take a large sample and we get this result. Well, probability that that's going to happen, assuming we took a random sample, probability that's going to happen is that it's 0.05%. Means 5 out of 10,000 times this is going to happen, which we would consider unusual, or rare if you prefer, and very, very unlikely. which means that either you took a sample in a sick ward in a hospital, an ICU, at a rock concert with a bunch of groupies yelling for their favorite star or something, right? Something got screwed up. Either the sample wasn't random, right? You just had really bad freaking luck, or there's something going on, and what we have here ain't exactly true. Either this is not true, or we screwed up the sample. Because this is telling me zombies are coming. All the zombies. Right? Now, most tables will have z-scores from about 3.5 to negative 3.5 to about 3.5. If you're asked about probabilities above 3.5 and you don't want to use the online calculators, you actually want to use the table for it. If you get asking about z-scores, about the rule of thumb says that if we have 3.5 here and negative 3.5 here, is that this area right here is 0.00001. Just put a very, very small number. Same with this one. This area right here is 0.00001. And then this area, all this up to here, is 0.99999. So this is one of those. Above 3.5 and below negative 3.5 z-scores, those areas are extremely small. Even if we look at our table that we found online, right? 3.5. 3.5 already is telling you that this is almost all nines, and then at 3.9 we assume it's almost 100%. So all this area at 3.9 becomes about 100%. And again, depending on which table you look at, those ones can show up earlier or later depending on how many decimal places they are. Right, so this is just a quick note saying that negative 3.5 to 3.5 is usually where we like to keep the whole thing going. All right, so this covers a big chunk of the initial chapter 4, and then next time we're going to be looking at confidence intervals and see how those behave and what we can do with those. Again, if you have any questions, just reach out and I'll try to answer them as best I can. Thank you and good luck.